Following the bouncing ball. In this lab, our goal was to determine the coefficient of restitution between two objects. The two objects we decided to experience with was a racquetball and a golf ball. The coefficient restitution depends on what material the ball is bouncing against. In this case, was a lab table. In result, the coefficient restitution we obtained for the racquetball was 0.893 and for the golf ball was 0.874. The uncertainties we obtained were 0.046 for the racquetball and 0.051 for the golf ball. To conduct this experiment, we used 1 meter stick, a racquetball, a golf ball, Firefox app, a lab table, and Google Sheets. The meter stick was used to measure the distance we would drop the ball from above the lab table. Each ball was dropped from the top of the meter stick, going down, bouncing from the table, causing vibrations. In order to detect the vibration of the ball being dropped, one's phone is laying on top of the lab table using the Firefox app to detect the vibration and the peaks of when the ball is dropped. We then repeated these steps for the second ball. Once each ball is done bouncing, the Firefox app is paused. The data was then collected from the Firefox app. We chose the downward spike before the vibrations for our data, as seen in the pictures. If we were to choose the higher peak, it represents the vibration from the table after the ball bounces back up. Once we collected our data, we then used Google Sheets to input the data.
As part of this lab, we needed to find the coefficient of restitution, which is basically referred to the ratio of the initial and final velocities that the two objects colliding together experience. In this case, the objects were the ball that we were dropping and the flat surface, which was the table, that in this case was considered a rigid surface because it didn't move, but it did have vibration that were read by the Firefox app as the peak right after the ball bounces off the table. In order to determine the coefficient of restitution, we first needed to rearrange one of our kinematic equations involving velocity, time, and position that then we could use to solve the velocity that this ball could experience during all the bounces. We found that the velocity when it is dropped and the velocity when it bounces off the ground and then comes back and hit the table again would be mainly the same. The only aspect that changes is the delta time. And then by having that information, taking into consideration that we're talking about the magnitude of the velocity, therefore it is a positive number, our coefficient of restitution was mainly based on delta time since 1/2 g was cancelled. So it's delta time 2 over delta time 1. And this says that the coefficient of restitution in this case depends on the material that the ball was being bounced again, because if the table wasn't a rigid surface, then the velocity wouldn't have been 0, and then this wouldn't just be depend on delta time. And this also helps to determine if this collision lost kinetic energy, because if this coefficient is 1, they mean that it's an elastic collision, so kinetic energy is conserved. But if it's 0, it means that it's in an elastic collision, which means that some kinetic energy was lost or converted into another type of energy. After we pick our 5 consecutive bounces from our Firefox graph, we plug those numbers into the Google spread to then analyze this data. We found that our numbers were pretty reasonable because the amount of time that the ball was experiences in the air was getting smaller as the number of bounces increases. Then we estimated our uncertainty, which was 0.02. We estimated this uncertainty by first finding two possible values that the ball could have started bouncing off the table and then subtracting that by 2, and that's how we got 0.02. Then we needed to find the change in time, and we found that by subtracting finals minus initial, and that's how we got those 4 values in yellow. And then we had to estimate the uncertainty of this time, We use the propagation of uncertainty, the formula for addition, and that's how we got that the uncertainty for the 4 change in time was 0.028. Now moving into finding the coefficient of restitution, we needed to perform the formula of division, which was the delta time 2 over delta time 1. And then we did that for the 3 values, and then we needed to propagate the uncertainty, which is by using the propagation of division, and that's how we got those values in purple. Now, in order to find the coefficient of restitution, which would be the same as the average of this division of delta time 2 over delta time 1, we found that coefficient of restitution was 0.893. And then in order to find the uncertainty for the average, we use the equation of sum of squares, and we use the propagation of division for uncertainty, which is basically the uncertainty of the value divided by the value, then square it, and then you multiply that by the value of the division itself. As you can see in this example, you can see the cells and the numbers that those values represent, and that's how we got the 0.0454. And then we use this second equation right here to find the uncertainty of the coefficient of restitution, which was 0.046. And the difference in those two equations is that we use the sum of squares of a set of values, and the value K6 through Ka represents the uncertainty of the delta time 2 over delta time 1, and then you divide that by 3 because it's 3 values. And then the 0.007, we got it from the average of the uncertainty of the change in time, and then you square that, and that's how we got the uncertainties in blue for the coefficient of restitution and the average of this division. Given a summary of our data analysis, we found that the coefficient of restitution for the racquetball was 0.093, and for the golf ball was 0.874, and the uncertainties for the racquetball was 0.046, and for the golf ball 0.051. These uncertainties and coefficient of restitution, they're very close to each other, and this might be by the material that they were made and how they behave against the surface that they were being bounced off or colliding with. In this case, was a rigid surface. In this case, the balls were dropped from a distance of 1 meter, and they bounces off the table in a vertical direction. Depending on how we determine a coordinate system, the momentum going down will have been a negative momentum, and going up or bouncing off the table a positive momentum. The momentum of the ball changes throughout the bounces, but the total momentum is conserved because we include the earth, the ball, and the table. Therefore, there's no external forces acting on it. When we released the ball from the distance of 1 meter, there was a weight force that made the ball drop and then bounces off the table. However, this weight force is within our system because it is Earth or gravitational force. However, kinetic energy was lost and it was not conserved in this system. We know this by analyzing our numbers. We said that the range of coefficient of restitution should be between 0 and 1, 0 being inelastic or completely inelastic collision, and 1 being elastic collision. The numbers are closer to 1, however, there are no 1. Therefore, some of the kinetic energy was probably lost or converted to vibrations, heat, sounds, and we know that it also could be deformation, and we noticed that the racquetball, since it has a different material, it probably experienced a kind of deformation. And we also know that it lost energy because the more the ball bounces, the less height it will reach. and this might indicate that kinetic energy was lost and converted to other type of energy, because the more the ball bounces closer to the surface, the less time and the shorter interval time it was between, and that means that the ball is not bouncing as high because it's losing energy, kinetic energy, in between bounces.
To summarize, our goal from this experiment was to evaluate the elasticity of a collision from two objects bouncing on a surface by calculating their coefficient of restitution after a collision. This value has a range that determines whether the collision is elastic or inelastic. Values of 0 are considered perfectly inelastic, and values of 1 are perfectly elastic. Since we performed a real-life collision, the coefficient of restitution should lie somewhere in between those numbers. In terms of accuracy, the coefficient of restitution values were very close to 1. The racquetball, as shown in the red circle, had a coefficient restitution of 0.893 with an uncertainty of 0.046. The gold ball, as you can see in the green circle, had a coefficient restitution of 0.874 with an uncertainty of 0.051. When it comes to balls, they tend to have a high coefficient restitution, which, as you know, points to a more elastic collision. Our overall results match the statement, as their accuracy compared to the value of 1 is high. The dataset of the time intervals also gave us an accurate measurement, which contributed to the calculations of the coefficient restitution values. Both the racquetball and the golf ball has similar coefficient restitution values, which indicates that there was a high precision between the two.